Hi, this is day 2. Now, what I want to talk about is cues. I made a mistake yesterday. So, hold on, let me switch to a pencil. Okay. So, with the cue, I originally had it so you would have a cue and it would have a data type and it would have a value, and these were both type variables. There's a problem with that, which is because it doesn't really solve the issue, because what I want to have at the end of the day is I want to have the thing I call a cat-T work group, which has a bunch of different cues in it for different categories of work. For example, disk. One might be for disk, one might be for I/O, one might be for CPU. One might be for CPU, one might be for network. And these queues could be different in certain ways. One might be backed by disk. So if it overflows, it can store items to the disk. Another one might be, LIFO. Another one might be FIFO. The queues basically should be open in what they can do. Now, if I have what I was thinking is that to have this variable dat here, that it would be data associated with the queue. Now, the reason that I wanted that is because that way, for like example, this queue backed by disk, if it had an issue where it tried to write to the disk, so the disk-based queue, the disk-back queue rather, if it tried to write to the disk and failed, I wanted the queue to stop itself, so it would basically just stop. And then it would also be able to report an error. Now, the problem is, the error itself has to be stored, and I was thinking of storing it within the data element of the queue. And of course, the problem with that is that if cat-T work group has to specify what dat is, so you could create like a list of queues here. So if I had like queues and made it a list, I would have to specify the dat field of the queue input. I could either keep it as a variable and put it up here, in which case whoever created the cat-T work group would have to specify dat, or I could specify it down here. The problem is in both of these cases it's wrong, because what happens is then every queue has to have the same data. And because I want the queues to be heterogeneous, I want to have some that are disk, some that are CPU, some that are network. They all might be different. Some might be FIFO, LIFO, so forth. The data is going to be different. So I can't do it that way. So what I need to do is I have to start with the restriction that the queue input, the only variable I can have is value, and that's it. Anything else has to be somehow included another way. So I went through several different ideas, and the one I came up with that seems to be the best is to, when you create a disk-backed queue info in particular, that you return not only a queue info, but also a T-var to an error type, an error status, or maybe just a status. We'll call it error status. So this would be in basically a tuple. And this way, the caller can watch the T-var error status, and also the queue info can watch it, and it can if the TVAR has an error, it can just stop. It can pause itself. Now that's one idea. The other thing I was thinking is, it doesn't really matter what the memory queue is. So in other words, like for a disk back queue, what it consists of is basically an in-memory queue, which might be anything. I mean, right now I'm just using a LIFO queue, and then a couple of basically just one thread. I think just one thread, which runs in the background and just checks to see, oh, is this queue X% full? And if it's X% full, then start taking items off and saving them to the disk. Save to disk. And then if it's empty, I mean, if it goes below a certain value, like let's say it gets up to here, gets up to here, and it's at Y%, or it's below Y%, then we start adding values to the queue. And I mean, it's a little strange because the disk back queue is going to do something in that it'll always add things in reverse order in the reverse of the order that it removed them. So if it removed, them in the order 3, 2, 1, then it would add them as 1, or 3, 2, 1, yeah, then it would add them as 1, 2, 3. And that makes sense for a lot of cases, I suppose. I mean, maybe it wouldn't make sense. I mean, if it was a FIFO queue, it would act kind of strangely. But even so, I think that it would be best if I could do this. I just figured out that, there might be a problem here because right now queues don't specify how full they are. There's no percentage. There's no way to ask a queue that. So I might have to go back to the original idea. But anyway, so that's my thoughts on that. One other thing I want to talk about is Whiteboard again. So Whiteboard is a way, I call it a calculation base, or a calc base rather than a database. So it's a calc base. And the idea is that you have some original data, and this original data gets turned into objects by an action. So it gets turned into some objects here, 1, 2, 3, 4, 5, whatever. And then the objects can write to more objects, and so on, and so on. One thing about it is it's a directed asymmetrical graph, a DAG. Okay, and that's important. And the reason is because I'm designing this system, this whiteboard system, that it should be fault tolerant. So if the disk becomes full, or there's an error writing, or a system crash, it should be able to recover and not return an incorrect result for any of the actions. All right. So the way that I'm doing this is that, let's take that thing again. I'll shorten it, only 3 items. Is that it takes these items and it puts them into what I call a journal. Okay. And then what happens is then it allows the items to go ahead and write to other items and read from other items as well. It can items can read from anywhere, actually. They can read, well, I'm not sure actually. Can they read from items that they write to it? I don't know. Anyway, I'll have to think about that. But they can read from items above them. That's interesting. This is not just a straight directed asymmetrical graph anymore. So they actually have, there's 2 graphs here. There's a read and there's a write. I'll have to think about it more. But anyway, so the idea is that we have a journal, and then we start doing work, and we store everything kind of in this disk-based LIFO queue, which I was just describing before. The LIFO queue. And once we're ready, like we'll run for like 5 minutes or something like that, a certain length of time. And then once we get to the end of that time here, we will start pulling everything off onto the disk. Everything goes to the disk, and then there's nothing left in memory. And then once that happens, then we can have the disk-based queue save itself, save its file to something to a new file. It's going to be like journal new, and then we move the journal new to the journal old, or to the current journal, And so this way, what happens is, no matter what state the system is in, because it's only writing to items that are below it in the graph, or further on in the graph, any changes that we make can be rerun using the old journal. So if the old journal, basically we had the queue, and the old journal worked against these 3 items here, and we started to write to a whole bunch of stuff, and we never finished. Then we crashed. This stuff is still there. It's in like a question mark state. I mean, X is not a good idea because it's still there. Hold on. Where's the button? There it is. Okay. So I'll just put a question mark here because we don't know what's going on. Then all we need to do is, when we start back up again, start back from the original journal, have it rerun, and since everything is pretty much functional, it never changes. I forgot the word for that, but anyway, everything's constant. So any function you run, action function you run, it will always return the same result. Okay. Actually, there's some exceptions to that, but we can talk about those another time, possibly, when I get to that part of the code. So that's how it works. And so then, if we have the original state, and then we have journal 1, and then after we process some, we might have journal 2, and so on and so on. And after journal 2 gets created, journal 1 gets destroyed, and we continue on in that way. And so that's basically the main way that Whiteboard is fail-safe, or it's supposed to be fail-safe. I've never written a fail-safe system before, so hopefully it'll work. I don't know. So after that, let's see. That's about it. That's all I want to talk about today. So anyway, talk to you tomorrow.